Imagine for a second that it's late. It's been a long day. Maybe you're just getting home, or maybe you're stepping out to take out the trash.
Right.
You step out onto the porch. It's a clear, crisp, let's say it's January 28th, 2026. You take a breath,
Mm.
and you look up.
And there they are, the stars.
Stars, and they look peaceful, don't they? They look frozen, fixed.
Like someone took a handful of diamonds and just, glued them to a ceiling made of black velvet.
Exactly. It is the ultimate image of stillness.
It really is. It's the classic image of eternity. Serene. Unchanging. For thousands of years, that is exactly what humanity thought they were looking at. A fixed, permanent backdrop to our lives.
Right. And that is the biggest lie the universe has ever told us, because the reality hidden in that stillness,
Oh, it's anything but still.
it is absolutely mind-blowing. It is violent, it is stretching, and it is tearing apart at the seams.
It really is a matter of perspective. I mean, what looks like a static painting to us is actually an explosion in slow motion.
An explosion in slow motion, I like that.
We are just so small, and our lives are so short, that we miss the drama completely.
So, today on the Deep Dive, we are going to unpack exactly how we figured that out.
We're going on the detective story.
We are. We're going to trace how humanity went from the Earth is the center of a static, boring box to we are living on the skin of a massive, expanding balloon that exploded into existence out of literally nowhere.
And maybe the most surprising part of this whole story, we're going to discuss how a pile of pigeon droppings,
Yes.
literal bird poop, was the final, crucial clue that proved the Big Bang.
I still can't get over the bird poop part. It's just too good. We'll get there, I promise.
It's the best part.
But first, let's look at what we're working with today. We have a massive stack of research, and it's all centering on a text that really bridges the gap between, hard astronomy and personal history. We're looking at the evolution of our understanding of the universe and referencing work by some of the absolute giants of physics, Friedman, Hubble, and of course, Stephen Hawking.
And what I love about this particular material is that it doesn't just give you the equations. It gives you the human struggle, the mistakes,
The fudge factor.
the fudge factors that geniuses like Einstein put in because they were scared of the truth their own math was telling them.
It really shows that science isn't just a clean march of facts, right?
Not at all. It's a stumbling in the dark until someone, somewhere, finds a light switch.
So, buckle up. We are diving into the expanding universe. Let's start with that illusion I mentioned, the fixed stars.
The great lie.
Yeah. When we look up, we see the planets, Venus, Mars, Jupiter, and those move. They move pretty visibly if you watch them over a few weeks.
They wander against the background. The word planet comes from the Greek for wanderer.
Right. But the stars, the Great Bear, Orion, they look the same today as they did to the Romans.
To the naked eye, yes. Absolutely.
Yeah.
And that optical illusion is simply a function of distance.
They aren't actually fixed.
Not even a little bit. They are moving, rushing through space at thousands of miles per hour, but they are so incredibly distant that from our perspective, we can't detect that motion.
But here's the thing that gets me, and it got the ancient Greeks too. If the Earth is moving, we're spinning at 1,000 miles an hour and orbiting the sun at 67,000 miles an hour.
Which is an insane speed.
It's a ludicrous speed. Why doesn't the sky look chaotic? If I'm on a merry-go-round, the world blurs. But I look up at the night sky, and it looks exactly the same as it did when the pyramids were built.
And that stillness is actually what held astronomy back for centuries.
How so?
Well, the ancient Greeks, Aristotle included, they argued that if the Earth moved, the stars should shift. They should appear to change their positions against each other.
It makes sense.
They called it stellar parallax. Since they couldn't see any shift, what was the logical conclusion?
That the Earth must be stationary.
Exactly. The Earth is still, and the heavens revolve around us.
And honestly, I would have agreed with them. It seems like absolute common sense.
It's a perfectly logical conclusion based on the available evidence. You could see it yourself. Hold your finger up in front of your face.
Okay, do it now.
Now close your left eye. And now close your right eye and open your left.
Yeah, my finger jumps. It moves against the wall behind it.
That's parallax. That's the effect.
So my two eyes are two different observation points.
Precisely. Now imagine your eyes are the Earth at two different points in its orbit, say in January and then in July.
That's a huge distance between the eyes.
Massive, about 186 million miles apart. So you'd expect a nearby star to jump against the background of much more distant stars, just like your finger jumped against the wall.
But they didn't see the jump.
They didn't. Not a flicker. And this is where the sheer scale of the universe just breaks our intuition. The shift exists, but it is microscopically small.
So small they just couldn't measure it.
It's like trying to measure the width of a human hair from a mile away. Their instruments weren't nearly sensitive enough.
So the Greeks weren't wrong about the geometry, they were just catastrophically wrong about the distance.
Precisely. They assumed the stars were just out there. Maybe a few million miles away, just beyond Saturn. They couldn't conceive that the nearest star is 25 trillion miles away.
Trillion, with a T.
So that parallax shift, the little jump, is so unbelievably tiny that we couldn't even measure it until 1838 with a telescope.
So for 2,000 years, the evidence of our eyes that the stars are fixed was actually just a failure of our imagination. We couldn't imagine things being that far away.
Exactly. And once we cracked parallax, once we could measure that tiny shift, we suddenly had a yardstick. And we realized just how terrifyingly large the void is.
Let's talk about that scale for a second, because the term light years gets thrown around a lot in science fiction, and I think we kind of lose our grip on what it actually means.
Yeah, it becomes just a number. It's a unit of distance, not time. That's the first thing.
Right. It's the distance light travels in 1 year.
And light moves at 186,000 miles per second. So in 1 year, it travels about 6 trillion miles.
6 trillion miles, okay. And our nearest stellar neighbor, the next star over, Proxima Centauri,
Is about 4 light years away.
so 4 times 6 trillion miles. 25 trillion miles.
That's something like that. It's a number that doesn't really mean anything to the human brain.
And that's the closest one. That's the house next door.
That's our front porch, cosmically speaking.
Yeah.
Compare that to our sun. The sun is only 8 light minutes away.
So if the sun just winked out of existence right now,
We wouldn't know for 8 minutes. We'd have 8 minutes of blissful ignorance.
but if Proxima Centauri blew up,
We wouldn't see it for 4 years.
Yeah.
The news travels at the speed of light. The scale is just instantaneous brain melt.
it really is. So, okay, we finally figure out that the stars are far away. We start mapping them. And for a long time, we figure out that most of the ones we can see are concentrated in this bright band across the sky,
The Milky Way.
the Milky Way. And back in 1750, astronomers are already thinking, hey, maybe this band means we're living inside a giant disk of stars.
A flattened structure, and Sir William Herschel confirmed that.
Right.
He painstakingly cataloged vast numbers of stars and realized we are in a spiral galaxy,
Yeah.
a flat, spinning disk.
But here's the crucial thing, and this is what I find so amazing. Until the early 20th century, the scientific consensus was that the Milky Way was it.
The whole ball of wax.
The entire universe.
The entire universe.
Yeah.
Just one island of stars floating in an infinite empty void.
But what about those fuzzy patches you see in telescopes, the nebulae?
The leading theory was that they were just gas clouds inside our galaxy, maybe new solar systems that were in the process of forming, swirling clouds of gas and dust nearby.
So the mental map was one galaxy, us, surrounded by an eternity of absolute nothingness.
Correct. A very lonely, but also a very grand idea.
And then comes 1924. This is the turning point. Edwin Hubble.
Yeah.
The man the space telescope is named after. And he just ruins that cozy island universe idea completely.
Hubble changed everything. Absolutely everything. He was using the new 100-inch telescope at Mount Wilson, the most powerful in the world at the time.
And he's looking at these fuzzy patches of light.
Specifically, he's looking at the Andromeda Nebula, the most famous fuzzy patch. And he managed to prove conclusively that it wasn't a gas cloud nearby.
It was another galaxy.
It was another galaxy, an entirely separate island universe, just like our own, millions of light years away, separated from us by a vast tract of empty space.
Okay, but how? How did he do that? If parallax only works for close stars, the finger jumping trick, and this thing is millions of light years away, it wouldn't shift at all. It would look completely frozen.
You're absolutely right. You can't use parallax on something that far away. The angle is too small to measure. He had used an indirect method, a much cleverer method.
It comes down to brightness, right? Luminosity.
Exactly. Think of it this way. If you see a light bulb at night, and you know for a fact it's a standard 60-watt bulb, you can get a pretty good estimate of how far away it is just by how dim it looks.
Sure, if it's blindingly bright, it's right in front of my face. If it's a tiny, dim little speck, it's way down the street.
Exactly. But the catch is you have to be absolutely sure it's a 60-watt bulb and not, say, a massive stadium floodlight that's just really far away.
Or a tiny little flashlight that's really close.
Right. Without knowing the actual wattage, the apparent brightness tells you nothing about distance.
You need a standard candle.
You need a standard candle. And Hubble found one. He used a specific type of star called a Cepheid variable.
These are stars that pulse, right? They get brighter and dimmer.
Yes, and here's the magic trick. A wonderful astronomer named Henrietta Leavitt had discovered that the speed of their pulse tells you exactly how bright they truly are, their intrinsic luminosity.
So a fast pulse means it's a 40-watt bulb, and a slow pulse means it's a 100-watt bulb. You have a key.
You have the key. So Hubble points his telescope at Andromeda, and he finds a Cepheid variable star inside the fuzzy patch.
So he sees this star pulsing. He times the pulse.
He times the pulse. He says, okay, based on its rhythm, I know this is a 100-watt bulb. But it looked incredibly, incredibly dim.
So dim that it had to be impossibly far away.
Way, way outside the boundaries of this Milky Way. He calculated the distance, and it was something like 900,000 light years. We know now it's closer to 2.5 million, but his number was enough.
Oh, it's enough to break the universe.
It shattered it. He calculated the distances to 9 different galaxies. And suddenly, the universe wasn't just one lonely island. It was a massive archipelago.
We now know our galaxy is just one of hundreds of thousands of millions of galaxies.
Some say trillions. And each of those galaxies has hundreds of thousands of millions of stars.
I feel small.
You should. We all should. Our sun is just a mundane, average-sized yellow star sitting in the cosmic suburbs, the inner edge of a spiral arm of the Milky Way.
We are definitely not the center of anything. We aren't even the center of our own quiet neighborhood.
Not even close. We live in the cosmic boonies.
Okay, so Hubble proves the universe is huge. Way, way bigger than we ever thought. But he didn't stop there, did he?
Not by a long shot. The next step was even more profound.
He started analyzing the light coming from these distant galaxies, and this is where we get into the rainbow connection, as you called it.
We do. And this is slightly more technical, but it's essential. You have to stick with us because it's the key to the entire mystery of expansion.
So we can't see the shape of a distant star, or a distant galaxy, really. It's just a pinpoint of light.
Right. But we can analyze that light. We can be detectives of light.
This goes back to Isaac Newton and the prism, right?
It does. If you pass sunlight through a prism, it breaks apart into a spectrum or rainbow. Now, if an object is glowing red hot, like the heating element on a stove or a star, it gives off a specific spectrum based purely on its temperature. That's the thermal spectrum.
But there's a fingerprint on top of that.
There is a chemical fingerprint.
How does that work?
Well, the elements in the star's atmosphere, hydrogen, helium, calcium, all the stuff it's made of, they absorb very specific colors of light. It's a quantum thing. They can only absorb light at certain precise frequencies.
So if you look at the smooth rainbow spectrum of a star, there are these tiny black lines where colors are missing.
Exactly, missing colors. And those missing lines, that pattern of lines, tells us with absolute certainty, hey, there's hydrogen here, or there's helium here.
It's like a barcode. Every star has a chemical barcode stamped on its light.
It is a barcode, a perfect analogy. And here's where it gets really weird. When astronomers started looking at the barcodes of distant galaxies, the pattern was there, but it was wrong.
Wrong how? Different elements.
No, the pattern was the same. The lines for hydrogen were there, the lines for helium. The spacing was correct relative to each other. But the whole set was pushed over.
Pushed over where?
Towards the red end of the spectrum.
This is the redshift.
This is the famous redshift. And to understand why that matters, why that one observation changes all of human thought, we have to talk about police cars or ambulances.
Okay, I've heard the term Doppler effect my whole life, but I admit I've never really understood how you can tell a star is moving just by looking at its color. A red star is just a red star, isn't it?
Well, no. This is where we have to decouple the idea of color, as in paint, and think of it as waves.
Yeah.
You know the Doppler effect with sound, right?
The ambulance thing. As it's coming towards you, the siren is high-pitched, and as it passes and goes away, it gets low-pitched, that classic meow sound.
Right, and that happens because the sound waves are physically getting squashed together as the ambulance rushes toward you.
Yeah.
That makes the frequency higher, a high pitch.
And as it moves away, it's stretching those same sound waves out.
Stretching them out. The frequency gets lower, so the pitch drops. It's a physical change in the wave because of the motion of the source.
Okay, that makes sense for sound.
Yeah.
Sound is literally air getting pushed around, but light isn't air, it's moving through a vacuum.
No, but light behaves like a wave. It has crests and troughs, just like a sound wave or a wave on the ocean.
And different colors have different wavelengths.
Exactly. Blue light has very tight, short waves, high frequency. Red light has long, lazy waves, low frequency.
So, if a star is rushing away from me,
It's literally stretching the light waves it emits as it travels. The space between the wave crests gets longer. So a color that should look blue or yellow gets shifted down the spectrum. It looks redder than it actually is.
And if it were moving towards us?
The waves would get squashed. Everything would be shifted towards the blue end of the spectrum. A blue shift.
And you can actually measure this tiny shift.
With incredible precision.
Right.
We know exactly where the hydrogen lines should be in the spectrum. We can measure how far they've been shifted to the red. It's a cosmic speedometer.
Police use this, right, with radar guns.
All the time. They bounce radio waves off your car. The shift in the returning wave's frequency tells them exactly how fast you're going. It's the same principle.
Okay, so Hubble and his colleagues, they start measuring the shift for all these new galaxies they found. What did they expect to see?
They expected to see a random mix, like a swarm of bees. Some moving toward us, blue shift. Some moving away, red shift. Some moving sideways with no shift at all.
Just a crowd of people in a train station, random movement in all directions.
Exactly. That's what you would expect in a static, eternal, chaotic universe. But that's not what he found.
Not at all.
In 1929, Hubble published a paper that was an absolute shock to the system. Almost every single galaxy he measured was redshifted.
They were all moving away from us.
All of them. The few that are blue shifted, like Andromeda, are our very close neighbors, caught in our local gravitational pull. But everything else, every distant galaxy, is running away.
And not just moving away randomly.
No, this was the killer blow. There was a law, what we now call Hubble's law.
The farther away a galaxy is, the faster it is moving away.
A galaxy twice as far away from us is moving away twice as fast. A galaxy 10 times farther away is moving 10 times faster. It was a clear, undeniable relationship.
Which leads to only one possible mind-bending conclusion.
The universe isn't static. It can't be. It is expanding.
And this was an intellectual earthquake. I mean, you can't overstate this, can you? Up until this moment, the smartest people in history, Newton, Einstein, they all just assumed the universe was static.
It was the default assumption. It seems obvious.
Why were they so sure? Was it just a philosophical bias, the idea of a perfect eternal heaven?
It was partly philosophy, yes, but it was also gravity. Newton knew that gravity attracts. Every star should be pulling on every other star. Every galaxy pulling on every other galaxy.
So if the universe were static and just sitting there...
Gravity should eventually pull it all together. It should collapse inward into one giant clump.
So a truly static universe is actually impossible because gravity exists. It's fundamentally unstable. It's like trying to balance a pencil perfectly on its tip. Eventually, it has to fall.
Right. But instead of concluding that the universe must be dynamic, expanding, or contracting, they tried to fix the math to fit their assumption.
This is where Einstein comes in.
This is where Einstein, in 1915, with his brand new theory of general relativity, was so utterly convinced the universe was static that he invented a fudge factor.
The cosmological constant.
Yes, he just added a new term to his beautiful equations, an anti-gravity force. He essentially said, okay, gravity pulls things in, so there must be some mysterious built-in repulsive force in the fabric of space-time that pushes things out, and they balance each other perfectly.
He forced the math to match his belief he cooked the books.
He absolutely did.
Yeah.
And he later called it the biggest blunder of his life.
Because there was one guy, a Russian physicist named Alexander Friedman, who didn't buy it.
Friedman is one of the great unsung heroes of this story.
He really is.
In 1922, 7 years before Hubble's observational proof, Friedman looked at Einstein's original pure equations for general relativity and said, let's take this at face value. What if we don't add the fudge factor? What does the theory actually predict?
And it predicted expansion.
It predicted a dynamic, non-static universe. He published it, and Einstein initially wrote a note saying Friedman's math was wrong, before later admitting Friedman was right.
And Friedman started from two very simple, elegant assumptions, right?
Incredibly simple.
Yeah.
One, on the largest scales, the universe looks the same in every direction we look. It's isotropic.
No special direction.
And two, that this would be true no matter where you were standing in the universe. If you hopped to a galaxy a billion light years away and looked around, it would still look roughly the same in all directions. It's homogeneous.
So we don't have a special seat in the cosmos.
Correct. And if you start with those two assumptions and apply Einstein's equations, the universe cannot be static. It must be expanding or contracting.
This brings us to the balloon analogy, which I think is the single best way to visualize what's happening. Because when people hear expanding universe, they think of an explosion into empty space.
Like a grenade going off in a big empty room.
Right. And that's the wrong image, isn't it?
It's completely the wrong image. If it were a grenade, there would be a center to the explosion, there would be an edge to the shrapnel, an empty space beyond it. The universe isn't expanding into space. Space itself is expanding.
Okay, so walk me through the balloon.
All right. Take an uninflated balloon, and on the surface of this balloon, you paint a bunch of little spots. Those spots are galaxies.
Got it. Balloon with polka dots.
Now you start blowing up the balloon. The rubber skin stretches.
Okay, the balloon gets bigger. The skin is expanding.
Now what happens to the spots on the skin?
They all get further apart from each other.
Right. But notice something absolutely crucial. Is there a center spot on the surface of the balloon?
No. I mean, the center is inside the balloon, in the middle of the air. But on the two-dimensional skin itself, no. Every spot is equal.
Exactly.
Yeah.
If you were a tiny, two-dimensional bug standing on one of those spots, you would see all the other spots moving away from you.
And if I hopped over to a different spot?
You'd see the exact same thing.
Yeah.
Every other spot moving away. There's no center of the expansion on the surface.
So just because we see everything moving away from us, it doesn't mean we're the center of the universe?
It just means we're on the balloon. An alien in a distant galaxy would see the exact same thing.
And the further apart two spots are on the balloon?
The more balloon skin there is between them that is stretching, so they move apart from each other faster.
That explains Hubble's law. The farther away the galaxy, the faster it recedes. It's not that the galaxy is flying through space faster, it's that there is more space being created between us and them every second.
It explains it perfectly. It's a beautiful, elegant model.
We aren't special. We aren't at the center. We're just on one spot of an inflating balloon, watching everyone else drift away.
Now you're thinking in 4 dimensions.
Okay, but Friedman's big assumption that the universe looks the same in every direction, that was just a guess when he made it, wasn't it? A philosophical preference. He didn't have the data.
It was a bold assumption. Justification by modesty, really. Why should we occupy a special place? But you're right. For a long time, it was just a mathematical model. It looked good on paper. It explained Hubble's data. But was it real?
Was the universe actually that uniform?
That proof, the final nail in the coffin for all other theories, came from the most unlikely source imaginable.
Yes. The bird droppings. This is my favorite part of the history of science because it's just so undignified and accidental.
It is 1965. We're at Bell Labs in New Jersey. And while all the great theorists at Princeton were arguing about the deep mathematics of the cosmos,
two guys, Arno Penzias and Robert Wilson, were just trying to get a clear phone signal.
They weren't cosmologists at all. They were radio astronomers, engineers. They had built this massive horn antenna, it looks like a giant ear trumpet, to balance radio signals off the first telecommunication satellites.
But they had a problem, a persistent, annoying problem.
They put on their headphones, they turned on their very sensitive microwave detector, and they heard a hiss.
Like the static you get on an AM radio between stations.
A relentless, uniform static. It was their day, it was their night, summer, winter. It didn't matter where in the sky they pointed the antenna, the hiss was always there.
Now, if I'm them, my first thought is, I built the machine wrong? There's a loose wire. A bad plug.
They assumed everything was wrong with their machine. For months, they troubleshot. They checked all the wiring. They taped over every rivet and seam with duct tape. They even, famously, looked inside the horn antenna itself.
And they found occupants.
They found a pair of pigeons had set up a nest and had left behind what the scientists later delicately referred to as a white dielectric material.
The famous white dielectric material, a beautiful euphemism.
It was bird poop. Lots of it. And Penzias and Wilson thought, aha, this dielectric material, the poop, it must be warm and it's radiating microwaves causing the interference.
You had a reasonable hypothesis.
So 2 future Nobel Prize winners spent their afternoon with brushes and cleaning supplies, scrubbing bird poop out of a giant horn antenna.
Science is rarely as glamorous as the movies make it out to be, is it?
Never. But here's the kicker. They cleaned it out meticulously, they evicted the pigeons for good, they turned the machine back on, and the noise was still there.
That has to be the moment the chill goes down your spine. Because if it's not the machine and it's not the bird poop...
And it's not the city of New York, because the signal was the same strength when pointing away from the city.
Then what is it?
Right. They did one more crucial test. They realized the noise wasn't coming from the machine, and it wasn't coming from the Earth's atmosphere. Because if it were, the noise would be stronger when they pointed the antenna at the horizon where you're looking through the most air.
But it wasn't.
It was the same everywhere, perfectly uniform. It had to be coming from outside our galaxy, from the universe itself.
Meanwhile, just down the road at Princeton University,
a team led by Bob Digg and Jim Peebles were working on this exact problem from the theoretical side.
They weren't engineers, they were the big-brained physicists.
Right. They were following up on the work of an earlier physicist, George Gamow, who had suggested that if the universe started with a hot, dense Big Bang, that incredible heat should still be around.
The afterglow of creation.
The afterglow. But because of the expansion of the universe, the balloon stretching for billions of years, that intense heat, that light, would have been stretched out.
Redshifted.
Massively redshifted. All the way from being white-hot visible light down into the microwave part of the spectrum. Dick and Peebles were literally in the process of building a machine to go look for this faint, cold glow from the early universe.
And then Penzias and Wilson called them up.
Penzias happens to mention his problem to another radio astronomer who tells him about the Princeton group. So Penzias calls Dick and says, hey, we have this weird, annoying static we can't get rid of.
And you can just imagine the silence on the other end of the phone.
The story goes that after he hung up, Dick turned to his colleagues and said simply, well, boys, we've been scooped.
They had accidentally found it. Penzias and Wilson had stumbled upon the cosmic microwave background radiation, the afterglow of the Big Bang.
That hiss is the oldest light in the universe. It's the echo of the creation of everything.
And it was the ultimate confirmation of Friedman's assumption, wasn't it? The radiation was almost perfectly uniform in every direction you look.
To 1 part in 100,000. It proved that on the largest scales, the universe really is the same everywhere. The balloon analogy holds up.
Penzias and Wilson got the Nobel Prize for that in 1978.
Which is, a little tough on Dick, Peebles, and Gamow, who actually understood what it was and predicted it. But that's the way history works sometimes.
Sometimes it pays to be the one holding the cleaning brush.
It really does.
So we have an expanding universe. We have the afterglow of the beginning. But that, of course, raises the big question. What happens next? Does the balloon keep inflating forever? Or does it pop? Or maybe. Does it deflate?
This is where we go back to Friedman. He didn't just have one model. He actually proposed 3 different models for the ultimate fate of the universe. And it all depends on how much stuff is in it.
So we know the universe started with a bang. We know it's expanding right now. The big open question is, does it ever stop?
This is the grand question of the fate of the universe. And Friedman's 3 scenarios, the best way to picture them is to imagine throwing a baseball straight up into the air.
Okay. I throw a ball up. Gravity from the Earth pulls it down.
Right. The throw is the initial expansion from the Big Bang, the initial outward force. And the gravity is the collective gravitational pull of all the matter, all the stars and galaxies pulling on each other, trying to slow the expansion down.
It's a cosmic tug of war.
It's the ultimate tug of war. So scenario 1.
Lay it on me.
Scenario 1 is the closed universe. This is where there is a lot of matter in the universe. So much that its gravity is very strong. You throw the baseball up, but gravity is strong enough to slow it down, bring it to a complete stop high in the air, and then pull it crashing back down to your hand.
The big crunch.
Yeah.
The expansion stops, reverses, and the universe collapses back into a hot, dense fireball.
Exactly. In this model, the geometry of space is curved back on itself, like the surface of the Earth. It's finite in size, but it has no boundary or edge.
So if you traveled in a straight line long enough, you'd end up right back where you started, like sailing around the globe.
Precisely. And in this model, time has a beginning and an end.
Okay. Scenario 2, the open universe.
In this scenario, there's not very much matter. Gravity is weak. Here, you have a superhuman throwing arm. You throw the ball so hard that Earth's gravity can't stop it. It slows down a little bit as it rises, but it has more than enough speed to escape and just keeps sailing up into deep space forever.
So the galaxies just keep flying apart.
Forever. This is sometimes called the big chill or the big freeze. Everything just gets further apart, colder and darker until eventually the lights go out.
And in this one, space is shaped differently.
Yes, it's negatively curved like the surface of a saddle, and it's infinite in extent.
All right. And finally, the weirdest one. Scenario 3, the flat universe.
This is the razor's edge, the Goldilocks throw.
Just right.
You throw the ball with exactly the critical escape velocity. Just enough energy to escape, but not a bit more. It flies upward, and it slows down and keeps slowing down. But it never quite stops, and it never falls back. It just coasts to a perfect alt at an infinite time in the future.
And space in this one is flat.
Just like the Euclidean geometry you learned in high school, it's infinite, and parallel lines never meet.
So which one do we live in? Is it the crunch, the chill, or the eternal coasting?
That is the multi-billion-dollar question in cosmology. To answer it, we need to know 2 numbers really well. First, how fast is the universe expanding right now? That's the speed of the throw.
That's the Hubble constant.
Right. And second, what is the average density of matter in the universe? That's the strength of gravity trying to pull it back.
We know the expansion rate pretty well, don't we?
We have a pretty good handle on it now, yes. The sources say the universe is expanding by between 5% and 10% every billion years.
But the density, the amount of stuff, that's the tricky part.
That is the great mystery.
Yeah.
Because we can only see the stuff that glows. Stars, galaxies, gas clouds.
And if you add up all the mass of all the glowing stuff we can see?
It is nowhere near enough to stop the expansion. Not even close. It's less than 1% of the critical density needed to make the universe flat.
So, based on what we can see, we should be in the open universe. Expand forever. The ball sails away, no question.
You would think. But for decades, we've known there's other stuff out there. Invisible stuff.
Dark matter.
Dark matter. We see its effects. We see galaxies spinning so fast that if they only contained the stars we see, they should have flown apart billions of years ago. There must be some invisible gravitational glue holding them together.
Like a halo of invisible mass around them.
Exactly. We also see it in clusters of galaxies. The galaxies are moving around way too fast unless there's a huge amount of extra mass we can't see.
So, okay, we add in all the dark matter we think is there. Does that give us enough gravity to close the universe?
Still no. Even when we add up our best estimates for dark matter, we only get to about 10% of the critical density needed to stop the expansion.
So the verdict is still expand forever.
Based on the evidence discussed in these sources, yes. The overwhelming evidence points towards an open universe. The throw is too strong, gravity is too weak.
But we can't be 100% sure there isn't more stuff hiding somewhere we haven't looked.
We can't be sure. But we can say this with confidence. Even if the universe is going to collapse, it won't even start to slow down for at least another 10 billion years.
So I don't need to cancel my weekend plans?
You are safe. The sun will swell up into a red giant and swallow the Earth long before the big crunch happens, if it happens at all.
Comforting, I think.
In a cosmic sort of way, yes.
Now, I want to pivot to something that seems to really bother people about all of this. The whole idea of a beginning.
G equals 0.
Yeah, the Big Bang implies a start time, an instant of creation. And that makes people uncomfortable.
It does. And historically, that was a huge point of contention in the scientific community.
Why? I thought science loved finding origins and beginnings.
Not necessarily, because a beginning smacks of divine intervention. It sounds a lot like Genesis. If there's a moment of creation, people immediately ask, well, who or what was the creator?
And the Catholic Church, for one, absolutely loved the Big Bang Theory.
They jumped on it.
Yeah.
In 1951, Pope Pius XII officially pronounced that the Big Bang Theory was in accordance with the Bible.
That must have made a lot of secular scientists extremely uncomfortable. They wanted a universe that was eternal, self-contained, no creation event needed.
Exactly. And that desire gave rise to the steady state theory. This was the main rival to the Big Bang, proposed in 1948 by Herman Bondi, Thomas Gold, and Fred Hoyle.
Hoyle was the one who actually coined the phrase Big Bang, right? And he meant it as an insult.
He did. He was mocking the idea on a BBC radio show, and the name just stuck.
So what was the pitch for the steady state theory?
It was very clever. They agreed with Hubble that the universe was expanding. They couldn't deny the redshift data, but they said, hey, maybe as the galaxies move apart from each other, new matter is constantly and spontaneously being created in the gaps between them.
Just popping into existence out of nowhere.
A very, very tiny amount. The math worked out to about 1 hydrogen atom per cubic kilometer per year. It's an undetectable amount, but over cosmic time, it's enough to form new stars and new galaxies to fill the voids left by the expansion.
So in their model, the universe would always look the same. The overall density would be constant. Same distribution of galaxies. Forever.
No beginning.
Yeah.
No end. The universe is eternal. It's a very elegant, very powerful idea.
It solves the creation problem completely.
It was a very good scientific theory for one reason. It was simple and it was testable. It made a clear prediction. And that's why it failed.
It failed the test.
Spectacularly. A team led by Martin Ryle at Cambridge did a survey of radio wave sources in the sky. He looked at strong sources and weak sources. Now, in astronomy, looking far away is the same as looking back in time, right?
Because of the travel time of light. If I look at a galaxy a billion light years away, I'm seeing it as it was a billion years ago.
Exactly. Ryle's survey showed that there were way more radio sources in the distant universe in the past than there are nearby in the present.
So the past looked different from the present.
The universe was different back then. It was denser, more active, which directly contradicts the core idea of steady-state theory that it always looks the same.
That was the first blow.
And then the cosmic microwave background, the Verdtooth discovery, sealed the deal. That was the knockout punch.
Game over. The hiss that Penzias and Wilson found proved that the early universe was incredibly hot and incredibly dense. You can't get that from a steady-state model.
So the Big Bang model wins. But there was one last desperate attempt to save the eternal universe, right? The so-called bounce theory. Yes, the Russians. Lifshitz and Kalatnikov. They were brilliant Soviet physicists, but like many, they really disliked the idea of a singularity, a point of infinite density at the beginning of time where the laws of physics break down.
They wanted to avoid it.
They tried to find a way around it. They thought, okay, maybe the universe was contracting in the past, heading for a big crunch, but maybe the galaxies didn't all hit each other at the same point.
Like a mesmerizing cosmic traffic jam where all the cars just managed to miss each other.
Exactly. They argued that maybe the galaxies had some sideways movement, some rotational velocity, so they would fly past each other in the dense center, swoop around, and then start expanding again. No collision, no singularity, just a bounce.
Did the math hold up?
For a while, it seemed plausible. It was a very complicated model. But then a young British researcher entered the scene. And this brings us to the real emotional and intellectual core of our deep dive today.
Roger Penrose and Stephen Hawking.
Penrose started it. In 1965, he was a mathematician, and he came up with a powerful new technique, using the theory of relativity to look at the structure of space-time.
Yeah.
He applied it to a collapsing, massive star.
A star collapsing under its own gravity.
Right. And he proved, mathematically, that it can't bounce. Gravity becomes so overwhelmingly strong that it traps everything, including light, in a region of space-time, a light cone, that shrinks down to zero size.
A black hole.
And at the center, a singularity, a point of infinite density and zero volume. Penrose proved that if general relativity is correct, a collapsing star must end in a singularity.
Now enter Stephen Hawking. And we have to set the scene here based on the story told in the source material because it's so powerful. He's a PhD student at Cambridge.
And he's just been diagnosed with ALS, motor neuron disease, Lou Gehrig's disease. The doctor's given 2 years to live.
I cannot even begin to imagine the psychological weight of that. You're brilliant, you're young, you have your whole life ahead of you, and you're told the clock is ticking and it's ticking fast.
He was deeply depressed. He stopped working. He just listened to Wagner and drank. He almost quit science entirely.
But then things stabilized a bit. The progression of the disease slowed, and he met a young woman named Jane Wilde. They fell in love, they got engaged.
And suddenly he had a motivation, a powerful reason to live and to work.
He needed a job to get married. And to get a job as a physicist, he needed a PhD. And to get a PhD, he needed a thesis topic.
He went to a lecture, heard about Penrose's new work on collapsing stars and singularities, and he had a flash of genius, a true aha moment that would define his entire career.
What was the insight?
He realized that the expansion of the universe is just the collapse of a star run in reverse.
Run the film backward. Instead of everything falling in, everything is flying out.
Exactly. So he thought, if a collapsing star must end in a singularity, according to Penrose's theorem, then an expanding universe run backwards in time must have begun with a singularity.
That is the connection. It's so elegant.
It is. Hawking took Penrose's powerful mathematical tools, which were designed to talk about black holes, and he turned them around and applied them to the entire cosmos.
And in 1970, they published a joint paper proving it.
Yes. Penrose and Hawking, together. They proved that if Einstein's general relativity is correct, and if the universe has as much matter as we observe, there must have been a Big Bang singularity. The bounce theory was dead. The eternal universe was dead.
And what does that mean precisely for the concept of time?
It means that time itself has a beginning. At the singularity, space and time are infinitely curved. All the known laws of physics, including general relativity itself, break down. You cannot predict what comes out of a singularity.
So asking what happened before the Big Bang is...
It's a physically meaningless question in this model. Time began at the Big Bang. There is no before in which something could happen.
It's like asking what is south of the South Pole.
That's the perfect analogy. You can stand at the South Pole, and every direction you step is north. There is no point on the Earth's surface that is south of the South Pole. The question implies a direction that simply doesn't exist on the map.
And before the Big Bang implies a time coordinate that doesn't exist.
In this framework, yes. Time is a property of the universe. It didn't exist until the universe did.
This was a huge, huge deal.
It was the definitive proof that general relativity, Einstein's masterpiece, predicts its own downfall. It's a brilliant theory, but it predicts that there is at least one point in the universe, the singularity, where the theory itself stops working.
Because the singularity is too big.
No, because it's too small.
Yeah.
Infinitely small. General relativity is the theory of the massive. Of gravity, planets, stars, curved space. But at the singularity, the entire universe is compressed into a point smaller than an atom.
So to understand it, you need the theory of the tiny.
You need quantum mechanics, the theory of the subatomic world.
And that is the great irony that the source material points out. Stephen Hawking, the man who co-authored the proof that the singularity must exist in classical physics, then spent the rest of his life trying to use quantum mechanics to prove that the singularity doesn't actually exist when you get small enough.
That's how science works. It's a process of destroying your own beautiful ideas to build better, more complete ones. The singularity is a giant signpost in the landscape of physics that says, new physics needed here.
So let's just recap this incredible journey we've been on.
Let's do it.
We started with a static, safe, eternal universe with the Earth at the center. We used parallax to realize the stars are far away. We used Hubble's standard candles to realize the universe is mind-bogglingly huge and filled with other galaxies.
We use the redshift in their light to realize it's all expanding. And not just expanding, but expanding according to a specific law.
We found the leftover heat of that initial explosion in some pigeon-infested antenna in New Jersey, proving the universe was once hot and dense.
We looked at the cosmic tug-of-war between that expansion and gravity, and concluded that the universe is likely to expand forever.
And finally, we traced that expansion all the way back in time to a single point, a singularity, where space and time itself began.
From Aristotle to Hawking in under an hour.
It really puts that view of the night sky in a different light. It's not a peaceful ceiling, it's a snapshot of the aftermath of an explosion.
An explosion that we are a part of. We're made of the debris. The carbon in our bodies, the iron in our blood, it was all forged in stars that lived and died in this expanding universe.
I want to leave our listeners with a final provocative thought that Hawking often hinted at. If time truly began at the Big Bang, and if asking what happened before is a meaningless question like, what is north of the North Pole?
Yes. Where are you going with this?
Does that mean the universe is the ultimate free lunch? If there was no time for a cause to exist in, did the universe just happen, without a cause? Did it create itself out of nothing?
That is the question that keeps physicists and philosophers up at night. And perhaps the answer lies not in looking out at the grand scale of the stars, but looking down into the bizarre, probabilistic world of the quantum foam. But that is a deep dive for another day.
Indeed it is. So next time you step outside on a clear night and look up, remember, you're not standing still. You're riding on the skin of an inflating balloon, racing away from all your neighbors, and the air around you is still humming, faintly with the sound of creation. Thanks for diving in with us.
Keep looking up.